Welcome back. So last time we were talking about op-amps and how we can use these golden rules to simplify their design. We talked about what an op-amp is. It's a very high gain differential amplifier, and we talked about how to use some of its properties such as high input impedance and very high differential gain to come up with two very simple design rules called the golden rules of op-amps. So today we're going to very quickly review that, and then we're going to fly through a few examples of how to use them to design very functional circuits. So let's get going. First of all, remember what an op-amp is. It's a high-gain differential amplifier, but from a design point of view, we typically don't think of it like that. We think about it in terms of what it does. So here's our op-amp, and we can define these golden rules. One of these golden rules is that the input impedance of V plus and V minus is extremely large. What that means is there's effectively no current drawn in, or I plus and I minus are approximately zero. Again, because of the high input impedance. The second golden rule is that we can wire this thing up in so-called negative feedback in the following way. So we have the output going possibly through some stuff, but eventually winding its way into the negative input. And this led to a stable configuration where V plus was about equal to V minus. So the way I like to say this is that V out adjusts itself to try to make V plus and V minus equal. Otherwise, this large gain instantly corrects for it. But that leads to an additional thing to keep in mind, namely that in negative feedback, although V out is trying to be equal to V plus, that voltage has to come from somewhere. So we'll call this 2B, that the op-amp is a powered device and that voltage has to come from somewhere and can only put out what is put in. So there are power supplies that aren't often drawn in these circuits that are always there. An op-amp is an active device, it needs power to operate. So although we don't often draw these power terminals, they always have to be there. In the last video, we designed a quick op-amp called a non-inverting op-amp. Now let's design a different type called an inverting op-amp, just to see how some of these golden rules apply and also to derive a very useful circuit. Let's have a look. So we're going to have some V in, and somehow V out should have opposite sign of that. And we start, like we do with many things in electronics, with a voltage divider circuit. So we have these two resistors, R0 and RF, and we have some intermediate point, which is going to be governed by the voltage divider equation. Now what we'll do here is a little trick. If I know the current through each of these resistors, I know the voltage dropped across them. And I want to create a well-defined voltage at that point that I can reference it to. What we're going to do is insert an op-amp as follows. So we've just snuck an op-amp in there, and what we're going to do with the plus terminal is set it to ground. Okay? And that's it. This is an inverting op-amp. Let's see how we can use the golden rules of op-amps to see how it's designed. So first of all, the golden rule about the current tells us that no current is flowing into V minus. Therefore, the current through the resistor R0 and the current through the resistor RF are equal. But if I know the current through a resistor, I know the voltage dropped across it. Furthermore, we have golden rule 2 that tells us that the node in between RF and R0 is equal to ground. So now I have a well-defined voltage at each side of the resistor. I know the current through it. I can figure out everything. I can figure out the voltages on each side of them. Let's do that. So we'll just use Ohm's law that tells us the voltage dropped across a resistor is equal to the current times the resistance. Now since these currents are the same, I can just write this in terms of the delta V's across the resistors. What is the voltage across the first resistor? Well, it starts at V in and it ends at 0. And the second resistor? Well, it starts at 0 and it goes even lower to V out. So writing this in terms of V out is equal to something, what do we get? We get that V out is equal to negative RF over R out, V in. If V in is equal to 5 volts and RF and R0 are equal, we'll get negative 5 outs. If V in is equal to negative 2 volts and RF is equal to R0, we'll get plus 2 volts out. So this is why it's called an inverting op-amp. Sometimes you call this term RF over R0 times negative 1 the gain. And the gain is simply V out over V in. That's it. That's the inverting op-amp. Let's move on to another op-amp called the summing op-amp. Now the voltage summing op-amp solves the following problem. Often in circuits we might have one input and another input. For example, one of them is a sine wave and the other one is an offset that we want to adjust. And we want to add those two voltages together. And when we're first starting electronics, the naive thing that we might try is to actually just wire them together like this. I have V1 and V2, I'll just put them together. And then I'll have V1 plus V2, right? No, in fact I won't. I'm actually trying to set V1 equal to V2 here. Because they're wired together, and by definition what a wire does, it holds an equipotential, it's actually trying to set these two voltages together. It will not simply sum the way that currents do. So this won't work. What if we actually want to sum voltages together? Well, there's an op-amp for that. So let's look at how we might do this. The problem is we have V1, V2, V3, Vn. We have n voltages, and we want to sum them all together for an output. The trick is we're going to first convert these to a well-defined current, and then we're going to add the currents up. Currents add up really easily because of Kirchhoff's laws, and then we'll convert that current back into a voltage with an op-amp. Let's see how we do that. First, we'll convert them to a current by adding a known resistance. Now, in order to have a well-defined current, I need to have a well-defined voltage drop across there. So what we'll do is we'll use our op-amp trick again to hold the other side of these at ground via negative feedback. Let's see how we can actually wire that in. So I'm going to create some kind of feedback path like this. This is my negative feedback, and we'll clamp the plus side to ground again as we did before. So now V plus is equal to V minus is equal to ground as before, and all these resistors are wired into that node, which appears to be ground. So we have a well-defined voltage drop across them. By the way, whenever you do this, this is called a virtual ground. What we've done is we've created a virtual ground right at this node here. Okay, let's look at the currents now. Because the other side of that resistor is ground, there's going to be a current flowing through each one of them, as long as V in is not ground, and that current has to flow somewhere. Now we know from our golden rule 1, that no current is going to flow into the op-amp, so it's forced through this upper resistor, which we've also set as R. So writing that down, the first golden rule tells us that the sum of I1 plus I2 plus ... plus IN is equal to I out. But now from golden rule number 2, we know the voltage on each side of those resistors. And because we know the current now, and the voltage on at least one side of each of these resistors, we can convert it back into a voltage. And we can do that just with Ohm's law. So let's rewrite that in terms of Ohm's law. At the output, we start at 0 and we drop to V out. At the input, we start at V1 or V2 or V3 and we drop to 0. And now, since we have an R on all of the denominators, we can multiply the whole equation by R, times it by -1, and let's see what we wind up with. We find that V out is equal to -1 times the sum of all the input voltages. And this is a voltage summing op-amp. If we want to be fancy, we can write it in terms of summing notation. And we've made a circuit which adds up voltages. So a couple notes about this. First of all, we might not want that annoying negative sign there. That's not a big deal because we've already designed a inverting op-amp. So we can just have a gain of -1 inverting op-amp after this, and we have a positive summer. Second of all, we might want to add some gain. We can do that simply by making the feedback resistor a different value from the input resistors. We can even do fancy things like change the value of the input resistors to have a weighted sum. But this is the basic topology of the voltage summing circuit. So great, we can scale voltages with our inverting and non-inverting op-amps. We can add voltages. I guess the next natural step is to subtract voltages. We will do that with what is called a differential amplifier. Now, this might sound redundant because an op-amp is a differential amplifier, but it is a differential amplifier with a uselessly high gain. Let's turn it into a differential amplifier with a gain that we can actually work with. So a differential amplifier, our goal is to have two voltages and we're going to subtract them. One reason we might want to do this, by the way, we want to be measuring something very sensitive, and we have two sensors and we're looking at the difference between them, perhaps the light difference or the sound difference. But there's a whole bunch of background noise that's pushing both of them up and down at the same time, and what we're interested in is the small differences, the little blips between them. We don't care about this overall gain, but if we look at the difference between them, we can isolate the small blips, the differential across both of them. And that's very useful because then we can amplify it and really zoom in on what's going on there. So how are we going to make a useful differential amplifier with an op-amp? Well, we're going to start with something we've already done actually. We're going to start with an inverting op-amp. So we'll proceed in the exact same way we did before. We'll stick an op-amp between those. But now instead of grounding V+, holding it at a virtual ground, we're going to reference it to some other voltage using a simple voltage divider topology. Just like that. So now the V+ is some intermediate voltage. What is that voltage, by the way? Let's just work it out. Using the voltage divider equation, we have V+ minus 0 over VA minus 0. Note that we don't often write these zeros because it's usually referenced to ground as it is here, but I'm including it here just to make the next step more clear. And that's equal to this ratio from the voltage divider equation. Okay, and that gives us V+. But we know from golden rule number 2 that that's also what V- is. So now we have a well-defined voltage at V-, which we can use to solve for V out. So if we look at the top, these two resistors also form a voltage divider. But it's not referenced to 0 anymore, it's referenced to V out. That voltage divider equation looks like this. So let's write that slightly differently. What I'm going to do to make things easier is I'll call this whole fraction here little r. And then I'm just going to rearrange this equation in the following way. But V- can also be written in terms of this little r, so this looks like this. Or, rearranging, we get, okay? And let's put that back into its original form. And we'll just put a side note here that 1 minus r is just r naught over r naught plus rf. And we have the following equation. We have the same denominator on both sides, so we can cancel it out, multiply both sides by R0 plus RF, divide by RF, and we're done. So let's scooch it up to where I had drawn these two differential traces before, because we ran out of real estate. So just moving this line up here, we have V out is equal to, it looks to be RF over R0 times the difference, which is precisely what we wanted. So we have a differential op-amp with adjustable differential gain now. And that gain can be 2 or 3 instead of 10 to the 4, 10 to the 5, or 10 to the 6 like it normally is for an op-amp. We can actually have a usable differential op-amp. So that's great. We've done adding, subtracting, scaling. We've done all the arithmetic we need to do with voltages. We're going to take it one step further for the final two circuits. We're going to do calculus with op-amps. So we've done a differential op-amp. Let's do a differentiating op-amp, i.e. we want an op-amp which takes the derivative of a voltage. It seems like a very difficult task at first. And what we have to do to get this to work is to use a different element, a different linear element aside from a resistor. We're going to use a capacitor. The reason this works, if we remember from how a capacitor actually functions, it's a device which can store charge, and the amount of charge you get per volt is called the capacitance. So we can write it this way. So we have two parallel plates, we've stored some charge, and the amount of charge we get per volt is called the capacitance. But we can reframe this in looking at rates of change. So at some point this charging has to occur. And if we look at how fast that's happening with time, well, how fast something is happening by time is what we call the derivative, d by dt. So let's take the derivative of both sides of this equation. The capacitance is approximately a constant, so we don't worry about it. And we get dq by dt on one side. What is that? That's the rate of charge per time. That's how much charge we get flowing through something per time. That's just the current. And that's equal to some constant c times the rate of change of the voltage across that capacitor. So this is another way of writing the defining equation for a capacitor. So let's actually insert our capacitor into an op-amp now. Let's see how we can wire this up. As before, we have some V in, and instead of running it through a resistor, let's run it through a capacitor. And we'll have a feedback resistor as before. Now notice that if we were defining this such that the output was between the resistor and the capacitor, and the arrow there that we're going to call V out was ground, this would actually just be a high-pass filter. But right now we're going to stick an op-amp between there as we have before. And we'll use the same virtual grounding trick that we have again and again and again. And I've called that V in, but I meant, okay, so this is exactly as it was before. We know the current has to flow somewhere. It can't flow in to V minus, so it has to flow through the resistor. Golden rule number 1 tells us the current through the capacitor is equal to the current through the resistor. But I have expressions for each of these. I know the voltage dropped across the capacitor is given by the above equation, C dV by dt, and I know the voltage dropped across the resistor is just IR. So we start at 0, as we did before, and we go to a lower voltage, V out. Let's actually write that down. So note that what is V across the capacitor? It starts at Vn, it goes to 0, so that's just Vn minus 0, and we just take the derivative of that, which is the derivative of Vn with respect to time. On the other side, we have Ohm's law, which is we start at 0 and we go to a lower voltage, so that's negative V out over R. Rearranging this, we get V out is equal to some constant RC, which has units of seconds, interestingly, times the rate of change of voltage with respect to time. And it better have units of seconds, actually, because the units of a derivative, something you don't often think about, is 1 over time in this case, because it's d by dt. So RC times d by dt times voltage gives us voltage again, which is good. So this is our output. So we get an output which is a derivative of the input times some scaling factor. If we want a very big derivative, we can set RC to be high. This seems like magic to me. So when I first saw this, I was kind of like, okay, I see the math, don't believe it. Let's actually try to wire one of these up and convince ourselves that we actually can create the derivative of a signal just by sticking an op-amp in between a RC filter. Okay, so here I have an op-amp circuit set up. This is a differentiating op-amp. I'm using an RC4558, basically a newer version of the 741 op-amp. I've used a 1 kilo ohm resistor, 1 microfarad capacitor, giving a time constant of about a millisecond, and we'll wire this up as a differentiator, meaning I'm going to put this pin to ground, and this pin here will be our input. It'll go to a capacitor, and then we'll have a resistor to this point here, and this will be our output. So that's what we have wired up here. The yellow trace is the input, the blue wire and the blue trace is the output. And I have a sine wave in. If I remember from calculus class, if I have V0 sine omega t, and I want to take the time derivative of that, I should get V naught times omega times cosine omega t. And a cosine is nothing other than a sine that's shifted by 90 degrees, or a quarter of a wave. And I have a term that's proportional to frequency. And we can see that's exactly what we get. We have a shifted sine wave. In fact, it's going to be negative here because it's negative RC. And hopefully if I increase the frequency, the wave will get bigger. So let's do that. I'll increase the frequency here. And you can see indeed, I get a larger derivative as the frequency increases, a smaller derivative as the frequency decreases. So that's great. How about other interesting waves? For example, the derivative of a slope, that's just like a function of the slope, that should be a constant. So if I have a derivative of a ramp wave like this, I should get just a series of constants. In other words, I should get a square wave. So let's program in a triangle wave, and indeed that seems to be what we get. There's a little bit of funniness along the edges, but in fact we can see the derivative is just the slope, and I'm getting the slope in each case. Again, if I increase the slope, it gets bigger, decrease it gets smaller. We can go totally crazy here and try to take the derivative of a square wave now. If I take the derivative of a square wave, well, it's going to be 0 almost everywhere, and then it's going to be infinite or negative infinite in these transition points. So let's see what happens if I do that. I'm going to plug in a square wave, and indeed I do get these delta function spikes. So this does indeed appear to be a differentiating op-amp. So we can take the derivative of a voltage. We can do calculus. The last thing we'll talk about is the antiderivative, also known as the integral. So let's take the integral of a voltage. And that's nothing other than swapping the position of the capacitor and the resistor. So what we're going to do is we're just going to put the R first and the C after and see what we get. Okay, so again, we'll use our golden rule to say the current through the resistor is still the current through the capacitor. But now through the resistor is the V in minus 0 over R. And the voltage across the capacitor is 0 minus V out. So our equation is kind of mixed up. It looks like this. Okay, so we can rearrange that, which is the derivative of the output voltage is some other constant, 1 over RC in this case, times the input voltage. And what we'll do is we're just going to integrate both sides. We're really pulling out the big guns. We're going to use the fundamental theorem of calculus, which tells us that the integral of a derivative of a function is just that function evaluated at its endpoints. So let's integrate both sides. And applying the FTC, V out of time is equal to minus 1 over RC times the integral of V in, plus the constant, which is whatever V out was initially. So maybe it was 0. It starts off at some point. It's just going to continue to integrate up. And this is the integrator op-amp. Again, let's wire that up and see what that looks like. So here's my integrator op-amp. Very similar to the differentiator op-amp. So if you remember, we had a resistor and a capacitor. And that capacitor was now across the feedback loop like this. And this is going to give us our integrator circuit. I've added one more thing. If you see here, I've added a switch on top here, and it's called a reset switch. It allows us to set V is equal to 0 at time t equals 0. That is that integration constant we had out front. And if I set this as closed, this capacitor is bypassed by the golden rules at this point, and therefore the output will be held at a virtual ground. So right now that's engaged. And I'll see something funny if I disengage it. So I'm going to do that. I'm going to start the integration of a sine wave, which by the way is another cosine wave, just with opposite sign. And I get it, but it runs away. The problem is my function generator is giving me a slight DC offset. So we can get around that by putting an extra little resistive load across the capacitor. But what I'll do instead is just kind of hack the system and AC couple it to remove any constant offset. And I do that, and look what I get, a sine wave that continues until it rails. So if I have a sine wave in, I'll get a cosine wave, and we can reset it at any time. And what we're seeing with this AC coupling is just kind of subtracting that DC offset. I can do the same thing with a square wave. The derivative of the square wave went nuts, but the integral of the square wave, well, it should just be integrating up a constant, up and down and up and down. Let's see that, and indeed that's exactly what's happening there. And finally, the derivative of a linear line, well, that's less obvious. But if I take the integral of a straight line, this is highly scientific notation, the integral of a straight line is a parabola. So I should get parabolas like this. It'll look fairly siny. So I'm going to send in a ramp wave, and I'll just start the integration, and that's exactly what I get. So there we have it, a circuit which integrates. Okay, so we've made a lot of op-amps over the past 2 videos. This sort of summarizes it here. We had the buffer op-amp, or the follower, which had V out is equal to V in. very useful because it buffers one side of the circuit from the other and can make a very favorable output impedance. We also modified that to have some gains. We had the non-inverting op-amp, so we had 1 plus RF over R naught was our gain. It couldn't go less than 1, but you could have a very high gain this way. To have a gain of less than 1, or at least a magnitude of less than 1, we made the inverting op-amp, which had the gain as just negative RF over Rin. And we can also put two of them together, by the way, to make a gain that is positive and less than 1. We also added up some voltage with our summing op-amp, and we subtracted them with our differential op-amp. Finally, we did some calculus and did the derivative and the integral using op-amps. All of these things, if you've noticed, all we did was apply the two golden rules. No current went into the terminals, and V plus was equal to V minus. That allowed us to design a whole vast array of op-amps, and there's many more that we could do, but these designs really show how you analyze any op-amp circuit. So I hope you found this useful, and until next time, thanks for watching.